Hello. In this video, I would like to show you how to analyze a heat exchanger, a simple heat exchanger using the SimScale platform. I will demonstrate how to prepare the CAD model, and in the end, I will show you how to generate such cool animations. Let's start with the CAD model. The original CAD model has only the tubes, but not the internal flow volume. We need to create the flow volume to be able to define the fluid types. You can use SimScale's CAD mode feature to generate the internal flow volume. As I said, we need to create a flow volume, expand the flow volume tree, and select the internal one. I need to pick a seed face. This is the face where should be in contact with the fluid, and the boundary face. Boundary faces shows where the fluid starts and where ends. The first fluid is generated. Now let's create the second one. This is inlet and this is outlet of the second fluid stream. I always recommend to use imprint because we will perform a conjugate heat transfer analysis, and we need to ensure that contacts are recognized correctly. Now export this updated CAD model to the workbench. The exported versions of the CAD model always come to workbench with copy of tag. Now this CAD model is ready to be used. Create a simulation, and now here select the simulation type. I will use Conjugate Heat Transfer version 2. This is the latest version of our conjugate heat transfer analysis. Contacts are automatically identified. As you see, green tick means that the contacts are identified correctly without any problem. I will use water, therefore it's incompressible. Radiation, solar, Joule heating effects will be ignored. There is in any way no Joule heating here. I assume the flow to be turbulent, so turbulence model is used, and I will test this in steady state because I want to know the temperatures in infinity. Fluid type. I want to have one hot stream, the internal pipe, internal fluid, and one cold stream. Let's say, according to the scenario I'm simulating, there is an excess heat from maybe a motor, and I want to cool the motor with seawater because seawater is colder. And I need to now define the materials for the heat exchanger pipes. I assume the pipes to be steel. By the way, this heat exchanger is only for demonstrating how to perform an analysis in SimScale. The values I'm going to use here, such as the velocities and the temperatures, might not be realistic. I don't mind, because I assume if you are a heat exchanger expert, you will for sure know your boundary conditions. I will define my boundary conditions now. As I said, this fluid will be the hot stream. I want to have a hot fluid, let's say 80 degree. I can define this velocity of this fluid, or I can define a flow rate. For this demonstration, I will just choose a flow rate, and I have one inlet to the hot stream. If I use one velocity inlet, I have to define an outlet to respect the conservation of mass. I choose a pressure outlet. I will do the same to the cold stream, a velocity inlet boundary condition. I want to have concurrent flow here, so I chose the inlet to be in opposite direction of the other flow stream. Again, I will use the same mass flow rate and temperature of 20 degree. Let's say that's the C temperature. And usually the heat exchangers are covered with insulation materials because usually from the heat exchangers the expectation is to extract some heat. But in this scenario, I want to simulate how to cool down a hot stream. As a result, I'm not going to add any insulation material. I chose the external faces of the heat exchanger. I want to define some convective heat transfer here. Temperature type, external wall heat flux, but instead of a heat flux, I will choose derived heat flux and define the convection coefficient. 10 is okay, sounds realistic. And ambient temperature 22. If you wish to add some insulation material around the external surfaces, you can choose wall thermal as layer wall thermal and define the thermal conductivity of the insulation material and layer thickness. But as I said, the purpose of this heat exchanger is to cool, and I'm not going to add any insulation material around. The heat exchangers external faces are directly in contact with the ambient. Alright, now you can define the number of iterations here. Just to keep this analysis short, I will define 800. This is a steady state analysis. Therefore, this end time is not literally time, but it defines the number of iterations. All right. Now I want to add some result controls. Means at the end of the simulation, I would like to see the result in a graph. I would like to measure the outlet temperature of the hot stream. And also I would like to measure the outlet temperature of the cold stream. If you wish, you can add observe turbulence and heat flux values. I'm not interested in them right now. I will leave the mesh settings as default too, but for such studies it is highly recommended to perform a mesh independent study. As a result, it's highly recommended to control the element sizes in your mesh by means of defining the global sizing and or adding some specific mesh refinements. Now I will simply press the hit button and run the analysis. There is no need to wait for the outcome of this analysis because I already did it earlier. This was my previous simulation where I used the identical settings and run the study. It took only 20 minutes with default processors. You can choose a larger processor to accelerate the analysis, but defaults are cost effective. Let's see, first of all, what do I do when an analysis is finished? I check the convergence. There are some convergence plots such as domain, inlet, outlet, and the walls. There I see how much each parameter is changed. In all around the domain, the temperature is increased and finally achieved convergence. Also, Z component of the velocity achieved convergence too, as well as the pressure. Velocity component of X has not achieved convergence yet, but I'm not really interested in that one, because in this demonstration demonstration project, I'm only interested in temperature values. Also, inlet data are also achieved convergence. The outlet 2, again, velocity has not achieved convergence, but that is not important for me right now. Wall temperature is 2, all right, and the residuals are reducing. Ideally, this should go down as much as possible. For this simple demonstration, residuals being below 1e-3 is okay. So let's see the temperature values at the outlet. The cold stream temperature is around, let's see, this is 290, almost 94 Kelvin. So around 22 degrees temperature of the cold stream at the inlet was 20. So we see that the temperature is approximately 2 centigrade degree increased. And because they had identical volumetric mass flow rates, I expect the temperature value at the outlet of the hot stream to change approximately 2 degrees too. Yeah, this is approximately 47, 48 Celsius. And now let's see the solution fields to do some post-processing. I will remove the existing results to show you how I generate the post-processing data. Okay. I want to define the colors based on some data. This is a heat exchanger. At the moment, I'm very much interested in the temperature. As you remember, the external shell I defined as a cold stream, and the internal from the central pipe there was the hot stream. We see that temperature at the hot stream is larger as expected. You can create cutting planes to see what is happening inside those pipes, and you can change the orientation of those cutting planes. So this is what's happening. I would like to add some vectors. Maybe reducing the spacing to increase the number of vectors here. As you see, the cold stream enters from this inlet and spreads around and leaves this system from the outlet. You see that this velocity gradient looks unrealistic. That's because the outlet and the inlet was pretty short. To capture the velocity, also correct pressure values, it's highly recommended to extend inlets and outlets so that we can capture the physics more realistically. All right, if you want, you can also check the mesh I did not pay any attention on the mesh, but it is highly recommended to pay attention on the layer sizes and also perform a mesh independence study to achieve realistic results. Because running a successful CFD simulation does not mean that the result is correct. You need to ensure that results are independent of the mesh size. Now, I will hide the vectors because I want to add something else. I want to add some particle traces. Click on particle trace and pick a position. I will pick this face as my seed face. It did not work. Let me try again. Pick face. All right. So these dots represent the seeds. So from all those dots, the particle traces will be generated. All right, I will choose another seed face, this time from the opposite face where the hot stream is. Okay. At the moment, I don't see the particle traces because on the screen the fluid regions are shown. I will hide the fluid regions now. Sorry. Flow regions. Okay. Again, due to the cutting plane, I'm unable to see the particle traces. I will hide the cutting planes too. Okay. Now the pipe thickness prevents me to see what's happening inside. What I'm going to do is adjusting the transparency of the metals. I can completely get rid of them too, but I prefer adjusting the opacity to make it more transparent. Also, I want to change the color mode of the solids here. I believe it looks more realistic if I choose the color of gray for the pipes. All right, so I have some. Let me hide the particle traces. This is the view of my solids, a transparent gray pipes. Now I will show the particle traces. This is the particle trace of the cold stream. What you see here is the particle trace is velocity. Also here the coloring is in velocity. This means the color is determined by the velocity values. I will switch to temperature. And I want to generate an animation, so I will use comets. Okay. Now let's do the same for the second particle trace representing the hot stream. Coloring temperature. And instead of cylinders, let's use comets. You can play with the number of pulses or the comet length, etc. and even the thickness. And now the comets are not moving. Let's create an animation. As default, animation type is a time step. The time step is important if you are using transient analysis, but what we did is a steady state. We do not have multiple time steps. We need to change the animation type to particle trace type. And finally, press the run button. If you want, you can play with the minimum and maximum temperature to make the Particle trace colors more intuitive. There are many stuff you can do. Just play with the post processor. Adjust the speeds or number of steps, animation speed. You can add ISO volume filters to see the specific temperature ranges in the model. There are many cool stuff you can do. And finally, you can record this and download as an animation or take a picture. Let me know if you would like me to perform any other analysis in a specific scenario.